Okay, hello everyone. I'm José Roberto, and today I'll be talking about a paper published in 2017, which is about magnetic bubble chambers and SubGeV dark matter direct detection. For starters, I still don't know what a bubble chamber exactly is, but it's not that important to the idea of the paper here. It's just it's based on a bubble chamber. Okay. This paper is mainly based on single molecule magnets. Okay, so it's a junction between kind of like a condensed matter field, condensed matter physics, with a little bit about particle physics. And this idea is very important, and several papers yet today are being published in this specific field. Exactly this week, a new one came out about axion particles. But let's go to the important part. So the basic idea is that we use a single molecule magnet crystal as a magnetic bubble chamber. Well, what is a single molecule magnet crystal? This is just a name for now. Well, that is just simply a crystal in which its molecules act as single magnets, which is straightforward. It's a crystal in which the molecules act as magnets. And not only that, but they are separated by regions which make them, like the molecules themselves, interact anomalously weak. So the interaction between them is very weak. So basically, this is the idea. You have here the single molecule magnet. Each one acts as a single magnet, and they do not interact very strongly with each other. Otherwise, the idea here wouldn't quite work. So the idea behind this paper is the following. We will prepare the crystal in an external magnetic field. Why is that important? Well, the crystal, so each magnet has a overgeneral spin J, and the polarization of the spin goes from minus J to plus J, which you have like 2J plus 1 possible polarizations. And the vacuum of the spin is degenerate. So this is basically the idea here. If you have a zero magnetic field, you can have both states in the single molecule magnet for each spin. This is for each spin, okay? So each spin respects this little thing here. And once you apply external magnetic field, you can have these two states now. You can see now that the most probable state in this case is the one with plus J, which is basically the state that aligns with the external magnetic field. But you still have this well here, this left well. Well, the idea is that if you don't have enough thermal energy, if, for instance, KT is way smaller than the difference between this minimum point, this local minimum, to the overall general minimum, you can have magnets in this metastable state. Why is this metastable? Because it is yet a minima, which satisfies the criterion of being as a possible state for the particle or the magnet to be in, but it's metastable because its most probable state is the one that is the global minima. Okay, the general idea is that if you're here, you can decay into the state via several mechanisms. For instance, if you have enough thermal energy, you can escalate this well and go back to this minima. And since we're talking about quantum particles, you can quantum tunnel to the other well. But the idea is that you don't have enough thermal energy, and quantum tunneling here is not that relevant. So you can put the magnets in this state, which is the important part, because once you have the magnets in this state, that means the spin not aligned with the magnetic field, the magnets will gain a Zeeman energy that once they flip, they release the energy. And the main idea here is that you can make them flip by making them interact with dark matter. So this is basically the idea of this image here. So as I said, let's suppose that this is the metastable state of the magnet. So you have a dark matter event happening here, whether that is absorption, whether it is scattering, it doesn't matter. and it gives energy to the spin, to the magnet. And once you give energy, you make them flip. And once they flip, they release the stored Zeeman energy, and this release of energy will give them energy to the next magnet. They will not interact magnetically, but thermally they can interact. So once you flip this two, you give energy to the neighboring magnets, and then you cause them to flip as well. And this is a process called as magnetic deflagration, which is kind of a spin wave happening here. You're flipping the spin of the whole crystal. And that is an important thing because you can detect this kind of stuff. If you have an external magnetic field, you can detect this kind of stuff happening. So this is a way to detect dark matter directly by these events. Okay, so the preparation of the materials, it says just you put the crystal on a tabletop, something, you put them in very low temperatures, and you apply a magnetic field and hope that they are in a metastable state. You can put them, but that's very specific, and I don't know exactly how you do that. But okay, so the idea is that once you don't have a magnetic field, the relaxation time of the relaxation is the flipping of the spin is very, very small. Once you apply the magnetic field, the relaxation time, I mean the time it takes for the spin to flip, is large, really large, around 10 to the 10 seconds. Okay, so it's long enough that you can have a long time of exposure expecting the interaction to happen. So that's very important. So you can see here.
Sorry, just go back a bit. Just go back a bit. Oh, 10 to minus 10.
Oh, no, this is when the magnetic field is not on and you have high temperature. This is, you see, if you have high magnetic field, the relaxation time is very long, month to years. Okay, and higher temperatures, you have this short thing. Okay, 10 to the minus 10. I was saying about with the magnetic field on.
10 to 10.
10 to 10, 10 to the 11. It's very long. It's somewhere it's somewhere in here. I don't know exactly. But
this relaxation is the time that
it takes the spin to flip.
On itself?
On itself.
Oh, okay.
So the relaxation time is given by this formula here, which is condensed matter field. And the important part of this formula for our treatment is this part here. This three here are described as, by said, quantum tunneling and temperature, energy, thermal energy and stuff. The important one is here. And this U is exactly the energy that we have minus the Zeeman energy, which will be released once the spin is flipped. Well, given that, the idea is basically that with an interaction, you can have, this is just the molecule. This is like specific things that are not quite important here. You can make them flip and cause an avalanche. Well, and we need it to be sensitive enough to the background. So why do we need this? Like, why is this important? Well, as we are aware, we still haven't detected dark matter, and yet we have billion-dollar experiments that are highly sensitive, and we haven't detected yet. So this is a tabletop, not that expensive experiment to detect dark matter, and it kind of gives us a good sensitivity for some models of dark matter. So in here, it assumes that we can have like a sensitivity to dark matter energy deposits of around 10 to the minus 3 electron volts to 10 electron volts. Okay, so this will be the basic threshold for us triggering magnetic deflagration process. Okay, so basically that's what will happen. We have the preparation of the detector. We prepare it at 0.1 Tesla magnetic field and 0.1 Kelvin temperature. Okay, then to the description of the thing itself. Let me find it here. It assumes in the paper that, oh God, where is it? Here. The heat capacity is at the heat capacity, which goes with T to the 3. It's a very simple model, but it states that it's pretty general for single magnet molecules. And so you can actually find out the difference in temperature based on the energy deposit here. And as I said, the important part is the exponential part for us, and you can put that in the formula, and in generally find the threshold here, which would be that the condition for the spins to flip is that the thermal diffusion rate is greater than the relaxation time. So why is that important? Because you need to have enough time for the heat once the spin flips to travel to other regions before it stays there. Okay, so that's the main idea. You put this condition here, and you find that the threshold energy here. What's up? No? Okay. The threshold energy depends on the size of the molecule, the crystal, the Zeeman energy, and on this tau naught here is a characteristic of the material. Okay, so it's something they get from experiments, basically. So basically, the important part is here. You can see that in the dotted and dashed here, and the dot dashed here are the ones when we do not have non-zero magnetic field. Okay, so you can see that it goes to the energy deposited here goes to almost negative values, which means that once you have a magnetic field on, you can have a very low threshold energy for the deposit. So it's very sensitive, which is an important thing to ask, like how sensitive it is for the energy deposits, because it's very important, because we're looking for a new region of masses of dark matter, because that's the important part. So once we do that, the paper itself assumes a dark vector model for dark matter, which is a model in which dark matter couples to our standard model photon through this coupling here, and kappa is a mixing angle between both. And this is the main interaction it will have with the standard model particles. Okay, that's the main idea. And then we have the rate of the interactions happening, which depends on the density of dark matter, mass of the dark matter, which is something we don't know exactly, so we can actually explore the parameter region, the density of the material, and the number density of the material. This here is the cross-section for absorption of dark matter. But in similar papers, we find that there is a relation between the cross-section of absorption of dark matter with the cross-section of absorption of a photon of frequency around the same mass as the dark photon here, which will be the vector dark matter.
In this case, is kappa effective?
Yeah, now
10 to minus 5.
Yeah, kappa effect something you can.
The square will be like 10 to minus 12.
Yeah, it's a few parameter that we are actually going to. What we are going to actually explore here is kappa. Yeah. What we're trying to do here is.
It cannot be like 1.
Right? Yeah, no, of course not. Because the region.
It's like the coupling of the dark photon.
Yeah, exactly. It relates to the coupling,
so
because.
It will be 10 to minus 6.
Here, there we go. That's the kappa effective. Kappa effective relates to kappa, which is the coupling, and the permittivity of the material, which is related to the experimental stuff. You can find it in papers, and that's it. Something it states here is that, well, we don't have a lot of these parameters for SMMs available. So while we have the permittivity for a specific SMM, which is this acetate, I don't know how to say this, honestly. For this specific SMM, we do not, the other parameters that are important, such as the U, that tau naught, which is related to the relaxation time, are not good for the specific detectors. But it's still, the paper studies for this specific acetate. I don't know how to say this specific chemical thing here, but it's not important. Yeah. Well, with this formula here, with the rate, there are a few papers that explore the rate of absorption of photons in this specific SMM, and then once we have the rate, and then we can find this as well throughout calculations, we can now put bounds on kappa. And that's the important part, which is this is specific graph here.
Yes, yes.
This is the
Oh,
key
even
point.
more than I thought. Like
Yeah,
10
yeah.
to minus 10 is just the capital.
This is the key. Oh, sorry, didn't show you.
Yes.
Okay, there we go. This is the key point. We have xenon 10 here, and the stellar bounds, they go up to 10 to the minus 15 around here. And with SMMs, we can go even lower on the coupling between the dark photon and the standard model photon, which is the important one, which what we want to do. We want more sensitivity. So this is the key point, the more important thing in this whole paper is this graph here, which is stating that if you have enough exposure here, so this is, we have one event per kilogram day here, and we have one event per kilogram year, and you get this two here, which is highly more sensitive than the other. The paper says that we can also find astrophysical bounds around this region here of couplings, but these would be stronger because it's something we control more in the laboratory, which we can extract backgrounds more easily than we can from astrophysical backgrounds. So this is the key important thing of the paper, and it's basically what I wanted to talk about. Just with this, we can actually get these two things, these bounds, new bounds.
That's nice.
Any questions? No questions.
I think just the point is, I think the time, the relaxation time is 10 to 6.
10 to 6, okay.
Because it will be a month.
But it says months to years. That's why I said 10 to 10.
Okay, but if you put 10 to 10, it is 300 years.
Yes? Oh, okay, sorry.
But anyhow,
10 to 6.
Just
Doesn't matter. Okay.
it's 3 is 4 factors.
10 to 6. I'm
no,
sorry.
But anyhow, it seems to be a nice paper, but it's quite similar to a dark photon model.
It's a dark photo model
Yeah, somehow.
here. It's the same Lagrangian here.
It's a dark.
Yeah, it's a dark photo model. Have a
they
Stuckelberg
mention-
mass. You have
They
this.
have a Stuckelberg mass, and then they.
The interaction with the standard model here, and then this.
Yeah.
Any questions whatsoever?
I wanted to know what is the U because I saw it.
The U?
Yeah, because
Oh,
I came here later, so I don't.
so it's easier to show the graph. Where is it? Where is it?
Because I saw that it's a temperature, but I wanted to know.
It's related to it. Where is it? There you go. U is the height of the. How do you say that in English? This o pico. Okay. So basically, is how much energy you would need.
Maybe it's the peak.
Peak could be to go from minus J to J in the case of a zero magnetic field. The main idea here is that it's the energy barrier found here. Barrier. Yeah, there you go. Any other questions? Okay, thank you. Thank you very much for the attention, and that's it.